So last time we talked two of the postulate, and which are kind of just intuitive. First one is that you need a postulate one is that you need a wave function to describe your system. And postulate two is that the meaning of the wave function is that it's a probability wave. Okay, the probability of finding a particle, or finding your particle at position x at time t equals to the amplitude square of your wave function. Okay, it's very simple. These are exactly the same as the Young double slit experiment you guys work in the homework. And now we move on to the third postulate. I want to be precise here. Given two possible configurations on a quantum system, okay, phi 1 and phi 2, or psi 1, psi 2. Okay, psi 1, psi 2 are different functions. Okay, the system will also be in everything's in the notes, so I'm not going to repeat it on the blackboard. Okay, the system will also be in a state the phrase is the system could also be in a state that is a linear combination of these two wave functions. Okay, it's just like a Young double slit experiment. You can have two states, and then the linear combination is still a possible state for the system. And here, since psi 1 and psi 2 are already complex number, okay, alpha and beta can also be complex number, because in the end you just take the amplitude and square. So complex number given the same amplitude will give you the same probability. Okay. So 1, 2, 3, the postulate 1, 2, 3 are kind of just the same as the light in a classical case. And of course here we show a very quick example that this postulate will lead to interference effect that give you the interference fringes in the double slit experiment for the electrons. Okay, for example, we can have phi 1 equals to phi k1x. It means a plane wave with a certain momentum. Okay, you can let phi 2 psi 2 equals a second plane wave with a different momentum. And we have k1 not equal to k2. Okay. And here, for simplicity, we just don't do the normalization. Okay, it's very natural that for plane wave, people leave the coefficient out because the coefficient is approaching 0. Okay, as we showed last time. So if you want, so the new state, okay, can be expressed as, let's say, just a linear combination of these two. Okay. So originally, for psi 1, you can see that because the amplitude is the same everywhere, okay, so you have an equal probability of finding your electron at any given position. The same here for psi 2. Okay, but then when you add them together and then you calculate the probability at position x, and this one you can just plug in, and then we work out as 2 plus okay, so you can do the math afterwards. So these two terms, what happened is that when you take the amplitude and do the square, you're typically doing psi 1 plus psi 2 times psi 1 complex conjugate plus psi 2 complex conjugate. Okay, so you have psi 1 complex conjugate. This one gives you 1. Okay, this one gives you the other one. Okay, and then now you have the what we usually call is cross term. Okay, psi 1 times psi 2 complex conjugate plus psi 2 times psi 1 complex conjugate. Okay, and this is usually not 0. Okay. And if you plot this out, probability x, okay, you find that, well, it's not normalized. Okay, so let's say probability not normalized. You find it very high here, and 0, and then it goes like this. Okay, so it's exactly the same as the interference pattern. Okay.
And x is not an argument of the cosine, right?
It is.
It is?
Yes. Yeah. And it's actually, whenever you calculate the probability, you always have to check that the number is a real number. Okay, that's why at the end we use cosine instead of, e. And you guys will practice a lot in the coming homework, okay, on this calculation. And the idea is simply to get familiar with that. Okay, it's okay to work in groups, and then maybe one of you come up with the solution first. That's totally fine, as long as you can follow the entire process, get familiar with it. That's okay. It doesn't have to be completely independent coming out from you. Now let's take a deeper look at the state we have discussed. We have discussed two states. One is, we say, a particle is at position x1, right? That's very classic state. You find the electron at a certain position. And we know that the way to describe this is its probability is a delta function. Okay, and again, delta function you need to work in the homework to really know what it is. And the other wave we talked about, another state, is also a kind of a very intuitive state. It's just a plane wave. Okay. And plane wave has, so for this one, the delta function state, this state has certain position. Okay. For this plane wave, it has certain momentum, right? Because we have said that momentum h bar k. Okay. So this state has certain momentum. Okay. Now let's ask a question. Okay. What is the momentum of this state? This is a little bit difficult. So let's see an easier one. What's the position of this state? A plane wave. The answer is you don't know, right? Because it's everywhere. Does that make sense? The probability of finding the position of your plane wave at certain location x is it's the same everywhere. Okay, missing a normalized factor here. So for this plane wave, let's say this is a real part. So for this plane wave, you have a well-defined momentum, but you don't know where the position is. Okay, so usually we say delta x, the uncertainty of the position, goes to infinity, because you can find it at 0, you can find it at infinity. So really, the uncertainty really approaching infinity. Okay, there's many different ways to approach infinity, but this statement is simply true. Okay. Yes.
This is the real part of psi squared x.
Psi. Square. No, let's put it this way. Let's say this is 0. Okay.
So it's a probability?
No. It's just showing cosine.
Is that one a probability? Top one?
That depends on how you. So their image is the same. Okay. But let's simply say it's probability. Okay. So here we know delta p approach the momentum is well defined, so the uncertainty of momentum goes to 0. Okay. But the uncertainty of the position goes to infinity. So here you already see the first example of uncertainty principle. Okay. For this plane wave, you know the momentum, you don't know the position. Okay. Now let's look back to this delta function here, a particle at a certain position x1. Okay, so what is its momentum? Right, momentum in momentum is h bar k, and then we know that h bar k is also equal to this one. Right, this is taught in the previous class. Momentum is associated with the wavelength of your wave. Okay. Now for this function, okay, does it have a wavelength? A wavelength means you move from x to x plus wavelength, and then the wave function repeats itself. Right, that's the definition of a wavelength. So here for a delta function, or for any function look like this, it doesn't have a wavelength. It's not a periodic function. Right? Only periodic function you can say there's a wavelength, because you need to move and repeat. There's no repetition here. Okay. So again, this one, lambda, the wavelength, we'll call it unknown. Okay. So p, because this is unknown, the momentum is also unknown. Okay. The momentum can literally be anything. Okay. So for this upper case, we have the position is very well defined at x1, so the uncertainty of a position approaches 0. But because it's not repetitive, you don't have wavelength, the momentum of your wave, the uncertainty of the momentum of the wave approach infinity. Okay, so this is another extreme example of uncertainty principle, where you measure one very accurate, the other very inaccurate. One very accurate, the other very inaccurate. And actually you can actually literally derive uncertainty principle by using wave. Okay, so this, once you assume the system is governed by wave dynamic, then the uncertainty principle is kind of a natural result. Oh, by the way, if you guys find these two classes too difficult, let me know, because I'm also experiencing how to prepare the class. I was told by a lot of my friends who are a little bit senior to me that I shouldn't prepare the notes in advance, because usually if I get too familiar with what I'm going to teach, usually people find that they will go too fast, and then the end result is that you prepare better, the class goes worse. So it even worked in Harvard and MIT. It's the same case that some of my senior friends there. They sometimes just walk into the class and then look at the note. Okay, here's what I taught today. And it happened to work very well. So these two classes, actually, I prepare like roughly about 10 hours. And then if it doesn't turn out very good, let me know. It also saved my time, right? Okay, so the next question is, let's say here, because these two extreme cases, you can tell momentum, also you can tell position, and then you can kind of also know the momentum, uncertainty of momentum, uncertainty of position. So now the question is, for any given wave function, okay, for any given wave function, for example, look like this. You can know the probability of its position, right? You always know the probability of its position just by doing this, by taking the amplitude and then square. But how do we know its momentum? How do we know its momentum? The answer is actually, I think every one of you are very familiar with this, is simply a Fourier transform. Okay, so the Fourier transform was actually invented by Fourier like way before quantum mechanics was introduced, and then I think at first people didn't really accept Fourier transform, but later it just showed it's really a powerful tool. And here, the idea was actually kind of transformed into quantum mechanics. The Fourier transform says any smooth well-behaved waveform fx. Okay, the definition of smooth and well-behaved is not the subject of this class. Okay, any waveform we use in this class is smooth. This function, okay, at that time people don't say a wave function. This function can be expressed as linear combination of plane waves. Okay, so mathematical form is fx equals to linear combination. Sum is also the same as integral. Okay, combination of plane wave ikx. Okay, these are all the plane waves with different k. Different k means different momentum. Okay, and because all these plane waves will have different, let's say, different amplitude or different contribution to a wave, right? So there must be a constant in front of this plane wave. Okay, it's like a weight function. And then you sum all this wave together, and the sum of all this wave are integration. Okay, it's the same as integration. Fourier transform is included in your mandatory mathematics class, right? Okay, good. And of course, we have the inverse Fourier transform, where you just flip. Okay. Okay, inverse Fourier transform. So this idea, not really idea, this mathematic form can be actually bring into quantum mechanics. Because in quantum mechanics, this plane wave has a physics meaning, right? It means something move with a certain momentum. Okay, the momentum of your wave is known. Okay, and the unknown part So physics version, okay, the physics version of this Fourier transform is the same thing, but just giving the meaning, okay? Give the meaning to all these things. We say any wave function notice that, well, kind of how people craft their language. Here we say smooth, well-behaved, because wave function is already smooth and well-behaved, so people drop that. Okay, and so any wave function psi x can be expressed as superposition of plane waves. Okay, so here notice the language change, okay, from linear combination to superposition. Okay, but they're the same thing. Okay, but when you go outside and talk quantum with other people, you always use superposition. Okay, you don't use linear combination for no reason, actually. And the mathematical form is this. Okay. So now let's look at this one. Okay, what it means, right? It means this wave function has a contribution from this plane wave with certain momentum k. Okay, and then the weight of this plane wave is described by this function. Okay, this number. For example, if we have ik1x plus eik2x, then for this function we know that it has half the probability of seeing a momentum of k1, half the probability of seeing momentum of k2. Okay, and then this Fourier transform is just an extension of this. Okay, you extend to infinite amount of plane waves. So
what is the squiggle on top of the wave function?
I just denote, this is just denote that this is a Fourier transform of this one. Okay. And okay. So the probability of, let's say, probability of measuring, let's do it this way. Okay. Let's give you a coefficient alpha beta. You can kind of see intuitively that the probability of measuring a momentum of k1 must be proportional to the amplitude of alpha squared, right? It's the same as measuring position, but here you measure the momentum because there's this probability that your wave is described by this plane wave. And then you have, well, we need to normalize it. Okay. P, the probability of measuring. Okay, the same apply to the second components. You just substitute alpha with beta, and that's the probability of measuring momentum with h bar k2. Okay. And then in reality, okay, what happened is that normally when you solve an equation, you first get something like this, a wave equation. And now when you want to know what's the components, what is its momentum components, then you do something like a reverse Fourier transform here, right? So you can tell okay. So with the wave function, which you already know, do this inverse Fourier transform, then you'll be able to know the amplitude of each plane wave. Okay. And let's work on an example. Let's use this on the delta function here, and also on the plane wave here. Okay. First one is a delta function. Well, the wave function is a delta function. Okay. This is actually not correct because there's some normalization issue here. Okay. But let's work on this first. Just neglect the normalization. And when we try to solve its momentum, you can think of it as you want to know the amplitude of each plane wave because each plane wave have a well-defined momentum. Okay, this one you just use inverse Fourier transform, and then delta x minus x naught e minus ikx dx. Okay. In the homework, you will kind of prove what this is with some hint. Okay, so it's not difficult at all. But here, let's make an argument of what this would be. Okay. For this integration, we know that integration is summing things together, right? Delta function is at its infinity at x equals x1, and 0 at all other places. So this integration have none. All the other parts are actually 0 except at x equals x1, right? let's say very small, x1 minus a small thing, x1 plus a small thing. Okay. Now this part is a little bit interesting when you do this integration. It's actually widely used in quantum mechanics. It's a mathematical tricks. Okay. It's a physics argument. We say that the wave equation is smooth and well behaved. What do we mean by that? We mean that this plane wave changed very little from x1 minus a very small quantity to x1 plus a very small quantity. It means that at this certain spot, okay, whatever wave function you're doing integration, it changed very, very little. Okay, that makes sense, right? So as it changed very little, you can take this as a constant and move it out to the outside of the integration. Okay, the mathematicians hate this, but it works every time. So you can take x equal to x1. And now because it's x1, it's a number, it's a constant, so you move it out. Okay. Minus it. Okay. And the integration of delta function, we know that it's 1, right? That's how we define delta function. We say integration from minus infinity to infinity is 1, but the only non-zero part is only close to x equals x1. Okay, so the integration of this is 1. So we know that okay. This is the momentum amplitude of this delta function. Okay, and then we can probably write it down as this. This one equals to, we already have 2 pi. Let's see. Okay. Okay, notice this part. Substitute this one in your Fourier transform. Okay. What it means is that this delta function is composed of a lot of different momentum. Okay. And then each momentum has a lot of plane wave with different momentum. Okay, and then each plane wave has an amplitude. It's this, and then the amplitude is always 1, right? It has a complex phase, but then the amplitude is always 1. So it means for this wave that looks like a delta function, you have equal probability of finding any momentum. Okay, the momentum you want to measure this momentum and that momentum. The probability of seeing them is equal. Okay, so that's why it's kind of mathematical proof that the uncertainty of a momentum goes to infinity. Okay, and in the homework, you will show that for this wave, the plane wave, you can do the same stuff, exactly the same stuff. And then you will show that this one is a delta function. It means that for the wave with k momentum, the probability is infinity. Okay, you're always seeing that wave. For all the other wave, it's 0. Okay, so you have well-defined momentum. And also in the homework, you would apply this to a kind of a more realistic situation that's a Gaussian waveform. Okay, Gaussian is always Gaussian. Well, the nice thing about Gaussian wave is that the Fourier transform is still Gaussian. Okay, so you kind of can do it again and again and again. Okay. And also the Fourier transform, there's a physics meaning of this one is that previously we say the postulate is that for any given two configuration of the system, their linear combination is still a configuration of the system. Okay. Here we say that if you're given you n configuration, their superposition is still a possible configuration. You can extract n to infinity. You know, this is this is a little bit unfortunate, but in quantum mechanics, if we want to get serious, we kind of have to go through this mathematical thing. Okay. Otherwise, the language is not even well defined. Okay. So now let's talk a little bit about this linear combination or superposition of. Okay, camera stop. Linear combination and superposition of the wave function. Okay. So first of all, we say that this two wave, when you combine, superposition two wave, we say that these two waves should not be identical to each other, right? Otherwise, you're just repeating yourself. It's the same wave. There's actually another condition that we use a lot. It's called orthogonal. Okay, two wave condition. Two waves are orthogonal to each other. Okay, we kind of need this because later, when we talk about operator, why each physics quantities are operator, we kind of need to go into this. Okay, so given a wave function. Okay. So think about this. Okay, if we don't give any restriction to this two wave, what is the probability of measuring the state? What is the probability of measuring the system in this wave function? Is it alpha square? Actually, no. Actually, no, you cannot say that. I can give you an example. Okay, if alpha 1 is e I k1x, okay, alpha 2 is e I k2x plus, let's say, half e I k1x. Right. So when you measure this wave function, you're also measuring some part of the second wave function because they have some part overlap with each other. Right? So when you want to measure this wave function, what happens is that you also take in this part. You're measuring alpha plus half beta square. This is the probability of measuring this wave function. That's the same as this wave function. Okay. So when you just give random wave function and then you build a linear combination, things become really complicated. You can't say the physics meaning of this and that. Okay, and it's a system that is not really well defined. Okay, so so now we have the following statement. We kind of correct this. Okay, we can correct this by saying if alpha equals, psi equals alpha psi 1 plus beta psi 2. And then each functions are perfectly normalized. Okay, so you don't have to worry about the normalization. And then we have this condition. Two wave functions are orthogonal to each other. Okay, later I will explain why orthogonal means integration. And then we can say the probability of system is in psi 1. Okay, the probability of your quantum system is in the psi 1 state is alpha squared. Okay, only when you have this condition satisfied, you can safely say that, okay, now the probability is very easy. You can just take the amplitude of whatever in the front and then say that's the probability. So how do people kind of find out this condition? It turns out it's our lovely friends from mathematics. Some people start working on linear algebra way before quantum mechanics. And then this is something called Hilbert Space. Okay, I would, yes?
So the probability of the system would be alpha squared? Or alpha, probability of system in psi 1?
Yes, probability of the system in psi 1. Yeah. So if you want to do this measurement, it's very simple. For example, if psi 1 represents a momentum, okay, then you simply measure the momentum. And then you see different value of the momentum, then you know the probability of this system in this state is associated with measuring momentum equals to h bar k1. Okay, so there's a measurement you can do to figure out the state of a system. So the definition of this, okay, comes from vectors. Okay, vectors. Okay, if you have a vector x1, y1, z1. Okay, you have a second vector b x2, y2, z2. Okay, each vector represents, if you in 3-dimensional space, right, represents something with the x, y, z. Represents something with the amplitude and then pointing towards the direction. Okay. And then the definition of these two are orthogonal, okay, perpendicular to each other, is A inner product with B equals 0, right? Everyone is very familiar with this. And this inner product also equals to x1, x2 plus y1, y2 plus z1, z2. Okay, it's a sum of the product of them. Okay, if you move to complex number, there's a way you can show that there has to be a complex conjugate in one of these. Okay, we're not going into that. And then one very important thing about this is that when you have two orthogonal vectors, okay, you can use it to express another vectors, right? You can write a C as a linear combination of A plus B, right? And because they're orthogonal, so whatever happened in the direction B doesn't affect the direction A, right? It's just like having a coordinate x, y, z. The value in x doesn't affect your value in y, doesn't affect your value in z. So that you can write down something as x, y, z. This is the same. You can think of these wave functions, each of them are like a coordinate. Okay, if they are orthogonal to each other, then you can write down its amplitude in the front, and then they have nothing to do with each other. Now, how does expand to here? Okay, this is something called Hilbert Space. What people do is that the linear algebra people, what they try to do is that they say, okay, we live in a three-dimensional world, but there are really no restriction on how many dimensions you can have, right? So you can have x1, x2, x3, xn, right? Your b can be y1, y2, all the way to yn, right? And then your inner product is just a sum of x and y. Yes?
C is not orthogonal to A and B?
No, no. It's like it's any vector. Well, the vector in the plane formed by A and B, any vector in the plane formed by A and B can be expressed as a linear combination. It's the same. You can think of this is the same as here. Okay.
Yeah.
Now, when you have, you can see now. See here, this one is already very close to the integration. By the way, this is 0 when you say it's orthogonal. Okay. It's sum of two product. Okay. And if you let n goes to infinity, means infinite amount of dimension. Okay. Then this one goes to integration of x and y and d something. Okay, dz. Let's say equals 0. And this one is just this one. Okay. It's the same definition as you will have in a three-dimensional vector. You just extend this definition into multiple dimensions, and then let the dimension goes to infinity. Okay, and then it will evolve into this equation. The actual proof of this is extremely complicated and was done by Hilbert. Okay, so it's called Hilbert Space. By the way, Hilbert is probably arguably the smartest person in the last century. Maybe him or Albert Einstein. Okay, Albert Einstein actually went to Hilbert to study some mathematics before he worked out his general relativities. So. So from here, you can see that in quantum mechanics, okay, you should always choose, when you write down your wave function as a linear combination of other wave functions, you should always choose orthogonal base, okay, orthonormal base, what we call it, because now the coefficient will have clear physics meaning, and then later we'll kind of introduce a method. Okay, a well-constructed method, how to make sure that you can get wave functions that are orthogonal to each other. Okay. Oh, by the way, at the end of this class, after the final exam, all of you would receive a complimentary T-shirt that says "License to Quantum Mechanics" by UVA, and since it's free, it would be made in Vietnam or made in Thailand instead of made in USA. Okay. If any one of you care, well, you can pay me $40, and then I can ask the US company to do it. Okay. Now, we'll start something extremely important and also extremely difficult from here. Okay. operator. From now on, the physics quantity are described by operator, okay, instead of by number. Okay, this is something extremely, extremely difficult to understand, and Heisenberg was the first one to figure this out. Okay, and Heisenberg was able to use this to build the entire quantum mechanics system without even using a wave function. And but the difficult thing is that the operator is more associated with linear algebra. Okay, and then at that time, physicists were not familiar with linear algebra, so Schrodinger actually got more supporters. Okay, and like in my own research, I rarely use Schrodinger equation. I use Heisenberg's method because it's just more handy in my case. Okay, now let's do this. Okay, operator. Again, we start with the wave function, a plane wave. Okay, with a well-defined momentum, well-defined frequency. Okay, if you think of P as h bar k and omega as energy as h bar omega, right? It has well-defined momentum, well-defined energy. Okay, just a plane wave. And one way to get momentum is look into this wave function and say hey, here's the k. This is your momentum. Okay, is there any mathematical way to extract the momentum from this wave equation? Let's say I want momentum times wave function. Okay, if I want this, then how can you get the momentum out? So Heisenberg was the first one to, well, maybe he doesn't use this wave equation anyway, but Schrodinger kind of at least uses this route, is that he says, okay, the idea is that I want to get the k out. Right? You want to get the k without looking into this wave function, without looking into the actual form of this wave function. So one thing you can do is that you can do a derivative of this wave function. Okay? For example, if you do derivative of x on this wave function, what you get is you will get ik. Right, you get ik in the front coming out. Right. So it's very interesting. Mathematically, this doesn't make any physics sense, but mathematically it works very well. If you want the momentum coming out from a wave equation, you simply do a derivative, and then you will have the k coming out. Okay? And because we know that any wave, we are already explaining, any wave can be built as a linear superposition of many, many plane waves. Right? So you know that this must work for general wave function. Okay? You just plus many, many other plane waves following this. Okay, so now there are some factors you need to fix here, right? So eventually people kind of agree on, it's showing here. Say if you want to get momentum, okay, what you can do is that you can take a derivative of your wave function. Okay, it gives you ik, but you want h bar k. That's your momentum. So time h bar, and then divided by I. Okay. It works for plane wave. Plane wave construct all the wave, so it must work for all the waves. Yes.
What's p psi? Like, what is that notation?
P is just momentum.
Yeah, but it's operating on psi.
No. This is a number, momentum.
Okay.
Yeah, the number of your the actual value of your momentum.
It's not a multiplication.
No. It's a simple multiplication, a number of times the wave function. Okay. And now this is a definition. Okay. Since this derivative, derivative is the operation on your wave function, right? You make integration, you make a derivative, you make second derivative. All of these are things you can do on a wave function. Okay, so we call this operation. So people define this part as a momentum operator. Okay. So when you do a momentum operator on a wave function, it comes out with the number of the momentum. Okay, make sense? This is directly from the fact that all the wave function can be composed of plane wave, and we show that for plane wave it worked. Okay, so it must work for all the functions. Questions here? Okay. We have only 5 minutes left, so we will skip the eigenvalue part. We'll talk about that later. And then let's look at the other things. In 5 minutes, you guys will see Schrodinger equation. Okay. So now let's say we want energy. We want to extract energy from the system. Then what will you do? This is very simple, right? The same thing. You do derivative of t, then I minus I omega coming out, right? You do derivative of t, then it's come out as I minus I omega. But the energy is h bar omega. So you have h bar here, and then I think you need another I, right? I times I equals minus 1, okay? So this gives you the energy. Do people call this energy operator? No, there's no such thing as energy operator. Now, this is the magical part, okay? Energy can also be expressed by momentum, right? If it's a free particle. Correct, right? What if I just let, you already see here, okay? I substitute this into here, right? I substitute the energy equals p squared divided by 2m. I simply use what is energy, okay, in this equation. Okay. And you change it to operator. The operation of this will give you momentum squared divided by 2m. The operation of this will give you energy. since energy equals momentum squared divided by 2m, this must be true. And this is the Schrodinger equation of free space. Okay, make sense? Energy equals energy. That's simple. Okay, so we'll talk a lot more about this in the next class, and we won't be solving Schrodinger equation for at least 2 more weeks because yes.
Is this kind of like a progression that like Schrodinger took, or like, oh, this must be true, so like do this, kind of like in a heuristic manner, I guess?
Yes. Yeah, Schrodinger did this, and then this is actually the second equation Schrodinger wrote. The first equation is now called the Klein-Golden equation. So Schrodinger first wrote that equation that's in special relativity form, and he used that to solve a hydrogen atom, and then he didn't get a spectrum, so he abandoned that equation, and then he later wrote this equation and solved the hydrogen atom spectrum. So he published this one, and a year later, Klein and Golden kind of think, well, why not extend this to relativity situation? And then they published that result. And it was later, I think, pointed out by Dirac or someone that Klein-Golden equation only work for boson. And electron is a fermion. So that's why Schrodinger didn't get the hydrogen atom. Okay. Otherwise, we'll have 2 equations called Schrodinger equation 1 and Schrodinger equation 2 if he wanted to publish both of them. Okay. Yeah. Okay, that's all for today. Okay.